All right. So let's continue our discussion on the mechanics of materials. So starting from the other document, the next document that I have sent to you, mechanics of materials, starting with the internal forces here. So first, let's just discuss the three type of internal forces that we deal with. You know that the vertical force would be called shear force. All right. The axial force called normal force, shown with N, and bending moment shown with the M as the internal bending moment. All right. So if I have a structure, if I cut the structure, all right, if I cut the structure from this location, so let me just show you, maybe I should have shown you the original beam first. So this was, for example, the original beam, right? All right. So on this beam, there was this force applied, and so this would be the case, right? So at this, so let's, if we call this like a point B, this point C, and a point B here, like at a specific location, all right? So if you are asked to find the internal forces at point B, you need to cut the member in that location. You cut the member, right? So when you cut the member, you're gonna have two structures separated, right? So you have the left side and you have the right side. So this is the right side. So this portion would be the right side. You have the two forces. And so at the location of cut, you need to show internal forces, right? At the left side, you have your reactions that you need to show. Right? To the reaction plus all the internal forces, right? So this would be your left structure. Okay, so these are two separate structures after you cut them. All right, so three internal forces and the other forces that can be support reactions or the external forces applied to your system. Okay. So let's look at what does it mean to find the internal forces at any location if you have like a real example to deal with. So let me erase this and go down here. All right. So in this example, it says determine the resultant internal normal force, shear force, and bending moment at point C. All right. So the problem is really telling you by saying this is asking you to cut the point of C and find the internal force. So if I cut at C, don't forget at this particular problem, doesn't matter if you select the left and right side, you're gonna see a reaction. So you need the support reaction. So we need to find the support reaction first. So here you have the By, here you have the Ay, and also you can have like a say that there's a horizontal force. It is equal to 0 because there is no horizontal force, but we can just like assume there. So summation of force in x direction equal to 0. So Ax equal to 0, nothing for that. So you can say summation of moment about like, I don't know, point A equal to 0, this direction positive. So for this one, you have the 60 kilonewton meters, right? It is counterclockwise, so positive. This guy is passing through A, no moment for this. This guy is creating moment, but it is counterclockwise, so plus By times 1 and 1 would be 2. And then you have this 100 guys goes down, come up from the other side, would be clockwise. The arm for that would be 1, 1, 2 would be 4. Nothing else equal to 0. From this By would be equal to. So the By from this would be 60 minus 40. All right, would be 60 minus 40 over 2 would be 10. But it is negative 10, right? It is negative 10 kilonewton, so it is less than 0. So it tells you the By really is 10 kilonewton, but the direction would be opposite of your assumption, so it would be a downward force. All right. Then we're gonna write summation of forces in y direction equal to 0, this direction positive. So from this we have AY, you have BY minus 10 kilonewton equal to 0. BY you have found to be negative 10. All right. From this, your AY has to be equal to 20 kilonewtons. It is more than 0, so the assumption is correct. This is alpha. All right. So let me fix it here. So I'm gonna show a downward force for BY to be equal to 10 kilonewton. The AY is 20 kilonewton, and this BX, sorry, let's just fix this one. This is BX. It is 0. All right. Everyone good for the support reactions? Okay. So if you don't mind, let me erase the calculation and cut at point C. So if I cut at point C, so this would be the cut point here. So if I cut there, it would be the left side and the right side. This is point A. This is point B, right? And this point of cut is point C. All right. What forces do you have? You have a 60 moment. You have a 20 force. Here you have a 10 force. Here you have a 10 force. All right. At the location of cut, you need to show the internal forces. So you need to go with the sign convention, outward positive for axial. For shear, you need to rotate it clockwise. You need to rotate the system clockwise to be positive, and the moment arrow upward. This is the left side. For the right side, outward arrow for axial positive. Shear needs to rotate the structure clockwise. So for this side would be upward. And also we have the upward arrow moment. All right. Either you can select the left side or right side, doesn't matter. I don't know, maybe let's just select the left side. So all right. So summation of forces in x direction equal to 0, this direction positive. So NC, no other horizontal force, so NC has to be equal to 0. Summation of forces in y direction equal to 0, this direction positive. So what do we have? We have 20 guy downward, sorry, upward positive. You have the VC downward, no other vertical forces equal to 0. So VC would be 20 kilonewton. All right. And then summation of moment. Usually the point that you have cut would be a good point to select the moment about point of C equal to 0. This direction positive. So what do I have? I have the 60 here, positive. You have the 20 about C would be clockwise, so negative. The arm for that, so this distance is 1, right? MC, VC both passing through C, but MC will producing counterclockwise moment. Nothing else equal to 0. From this MC is equal to 16 minus 20 would be 40. Go to the other side, negative 40 kilonewton meters. Okay. So these are your internal forces. Even if you select the right side, you would find exactly the same answers. Doesn't matter. All right. And something also you want to pay attention for internal forces, always we keep the signs as is. You don't define if it is otherwise or right, whatever. You just keep the sign as is. You don't change the signs. If it is negative, you keep it negative. Positive, you go with positive. All right. So let's just go, continue. All right, so how we can draw the shear and moment diagrams? There are a couple of important points. I want to go quickly through them. So in overall, the objective is to go from the load equation to shear equation to moment equation, or from moment to shear, then to the load, right? So we can go this way with different directions, really. All right. So some tips for us to know is that slope of shear diagram would be the distributed load intensity at each point. Change in shear is area under the distributed load. Slope of moment diagram, shear at each point. Slope in moment diagram is the area under the shear diagram. Regions of concentrated force when the force acts upward on the beam. There is a jump upward, and if the force is downward, there is a jump downward in the shear diagram. All right. So let's look at some examples here. So look at these examples. It would be good, actually. That would be better than writings, really. So this is a shear diagram, right? This is a shear diagram. This is a moment diagram. Look at this. If I have a force, usually first of all, I go from left to right. This is the direction you draw. You go from left to right. There is a concentrated force. So this force causes a jump in the shear diagram in direction of the force. Force upward, upward, jump, right? The area under the load would be the change of shear between 2 points. For example, this point and this point, right? What is the area between area under the load here? If you think about the area under the load is 0, right? There is no distributed area. The area under the load is 0. Okay? Area under the load is the change of shear. So it means change of shear between this point and this point is 0. So you go constant. Let me write it on top. Change of shear is area under the load. Mathematically, does that make sense for you? Change of shear is area under the load. Okay? Let's continue. You reach to this point. There is a downward force, P. You know that there is a jump because of this force. You're at 2P. 1P down, you're going to reach to the elevation of P here. All right? Because of the point load. All right? Then you are at this point. Again, the area under the load is the change of shear. What is the area under the load? Nothing. There is no area under the load. So there is no change in shear. You go constant. All right? You reach to this point. There is a downward P. So you know that there's a jump. You are at positive P. You go down P, you're going to reach to 0. Positive, positive. This is your shear diagram. This is the fastest way to draw a shear moment diagram, knowing this couple of keywords I'm keep telling while I'm solving this problem. It would be really just make this so easy. All right. Let's go to the moment diagram. I start from left to right. There is a concentrated moment. There is a concentrated moment. So it will cause jump on moment diagram. You have 3PL. It is counterclockwise. So counterclockwise moment leads to negative jump. In moment diagram. clockwise moment, positive jump in moment diagram. All right. So look at this. I have counterclockwise moment, so there is a negative jump. So from 0, I negative jump to 3pl, which is the value of that moment. All right, so I'm at this point. So the change of moment, look at this is very important. Change of moment between this point and this point is area under the shear diagram. All right, so what is this area? Is 2p times this length. We would say, I think it is L over 2, right? The whole thing is L. Is L over 2. So would be what? Would be PL. Okay? So it is a 2p times L over 2 would be PL positive. I think this is incorrect here. It is going to be, let me see. So if it is a P and L, all right. So the moment here would be P over 2. So this is incorrect here. Sorry, guys. This is gonna be, this has to be negative 2pl, right? Because the area here would be 2p, height, length would be L over 2. So 2pl over 2 would be positive pl. So you're at negative 3pl. Plus pl, you're gonna end up with 2p, negative 2pl. You got here, negative 2pl, all right? Order of this line is 0. Order of this line is 1. So you go with this straight line, okay? That happens when we don't put the dimensions on the beam. So if it is PL, so each of these guys is L, I think based on the way that it is written. So PL plus PA, it is each of them at L, all right. All right, well, that's something to learn, that always we need to show the lengths. I mean, lengths would be an important factor, very important factor. So we cannot just jump into the answers. So this would be an L, this would be an L. All right. So if you make it in an L and L, all right. So this area would be 2p times 1L. All right. So now it would be 2pl. All right. So you're going to change 2pl. You're at 3pl. You change 2pl positive, you're going to end up with negative pl. So it is correct. All right. You're at negative pl. Now, the change of moment between this point and this point would be area under the shear diagram. What is this area? It would be P times L. All right. So you are at negative PL. You change positive PL, you're going to reach to 0. Order 0. Order of this line is 1. All right. Negative, negative. The other equation that I was using, what was that? It was delta M is integration of V dx. All right. So change of shear is change of moment is the area under the shear diagram. So make sure that these two equations would be something you would be using. All right. So let's continue on an example. All right. Let's see. This is an example here. We want to draw the shear and moment diagram. All right. So I'm starting from left to right. Okay. So LL, this is the reaction, right? And this is a reaction. It is already calculated. We have this configuration. All right. For shear diagram, draw here. From a moment diagram, we are drawing here. So start from left to right. You are starting from left to right. All right. You're starting from here, sorry. There is a downward force. So there is a jump in shear diagram equal to that m0 over 2L. So you go down to this value. So you're gonna have you're at the negative point right now. So the area under the load is 0, right? Area is 0. So there is no change. So you're gonna go straight up to this point. No change. All right. You reach here, there is no like a point load or something. So again, you're gonna go from this point to this point, the area under the load. There is nothing. So no change in shear. So you're gonna go straight. All right. You reach here, there is an upward force of m0 over 2L. You go up, you reach to 0. Okay. Negative. This is the shear diagram. For moment diagram, you start again from the left side. There is no point moment or something. You start from 0, right? The area under the shear for this portion is what? If you think about it, it is negative m0 over 2L times the length is L. So would be what? Would be negative m0 over 2, correct? So this, you're gonna reach to m0 over 2. So the question is that, all right, do I go with a straight line? Do I go with like a concavity up, concavity down? Which way I need to draw the line? Because you know the points, but you don't know how to connect it. So you look at this one, the order of this guy is 0. The order of this one has to be 1 higher, 1. So that's a straight line. Okay. So you reach at this point, there is a concentrated moment. So you know that there is a jump in the moment diagram. It is clockwise, so it's a positive jump. You are at negative m0 over 2 plus m, you're gonna go to positive m over 2. All right. We are at this point, the area under the shear diagram is what? The area would be negative. Again, it would be m0 over 2L, right? Times L would be negative m0 over 2. So you have positive m0 over 2 minus m0 over 2, you're going to reach to 0. Again, your question is what way to draw this line? Order 1, order 2, concavity up or concavity down. All right. So order of this line is 0. So order of this one is 1 higher, 1. So this is correct. All right. This is the moment diagram. Positive, negative. Questions? Okay. So let's go talk about the concept of a stress as well. So the stress and the strain. No, the stresses are divided in 2 types. So we can have normal stress, we can have shear stress. Normal stress is usually shown with sigma. It is the normal force over cross-sectional area. Shear stress is usually shown with tau, which is a shear force over cross-sectional area. It is applied. The 3D stress cube looks something like this. So as you can see, this direction of the normal stress, sigma x, sigma y, sigma z, 3 normal forces, right? Normal to each of the planes, right? And then inside each plane, we have 2 stresses, right? 2 stresses, tau xz, tau xy, tau yx, yz, zy, and zx, all right? So when we say tau something by something, this one, it means that at what plane the shear stress exists. This one is towards what direction. For example, when I say tau xy, it means it is in the plane of x, which is this plane, right? Towards the y-axis. So at this plane towards the y-axis. So this is the one, right? Or one of them to be tau yz. The plane of y is this, right? And goes toward the z. So it would be this one. Let me show the black probably. It would be this one. This is tau y. And the second one would be, so it goes toward the z axis, for example, right? The next one, tau zy or zx, I don't know, tau zx, for example. If you go with tau zx, right, the z plane is this, all right? And the second one is towards, so it is like this and goes toward the x-axis. So this is your tau zx. All right, so that's how we name the shear stresses. What plane towards what direction? X, Y, Y, Z. So we can just understand it now. All right. So let's continue. Another type of stress, it is not the type, it is something that causes a stress. So torsion, the concept of torsion creates shear stress, right? The concept of torsion creates shear stress. So these 2 types of stresses are introduced here are the fundamentals, 2